So in this example problem, we're asked to replace the two couples that are acting on this pipe column system by a resulting couple moment. So we are given, we want to determine our resultant couple moment due to the moments that are applied at points A and B, the forces that are applied at points A and B, which will create a couple moment, MAB, plus the couple moment created by the forces applied at points C and D. All right. So to find our resultant moment, we first have to find our couple moments due to AB and CD. So let's start with AB. All right. So we can find MAB by using this equation. All right. So let's find the total magnitude of our couple moment first. At points MAB is going to be equal to the force times the distance at points B and the distance that separates points A and B. So that's going to be equal to 150 newtons is our force. And then the shortest distance between our two parallel forces is given to us as 0.4 meters. Okay, so that would give us a value of 60 newton meters. Okay, now we need to calculate what UAB is. So UAB we know will be perpendicular to both F and D. Okay, and so we can use the right hand rule. So remember, your fingers are is the force, represent the force vector, and then your palm represents the position vector, or in this case represents D. So our palm would go along the positive y-axis in this case. All right, and our force would go along the positive z-axis in this case. All right, and that would give us that would cause our thumb, using the right hand rule, to go along the positive x-axis. All right, so since it's going along the positive x-axis, all right, MAB, the vector MAB was going to be equal to it's going to be equal to 60 newton meters times I. All right, so that's our first one down. All right, so our second one will be a little bit trickier, but it's going to follow the same principle. Okay, so MCD. All right, we can use we're going to use, for MCD, we're going to use a vector formulation to calculate it. So what we can do here is we can say MCD would be equal to R DC cross FC. All right, so we define RDC and FC as Cartesian vectors. So we'll do that. We'll define them inside of our cross product formula. So from point D to point C, all right, that goes along the x-axis, and it goes along the positive x-axis. So it'll just be equal to 0.3 meters. All right, and the rest of it will be just 0 and 0. All right, and then FC is going to be equal to, based off of the diagram that we were given us, it's in the YZ plane, so it won't have an X component, so we'll have 0 in the X. 3/5 of it, 4/5 of it is going along the positive X-axis, so positive Y-axis, so it'd be 4/5 times 125 newtons times J, plus the 3/5 of it is going along the negative X-axis, so it'll be minus 3/5 times 125 newtons times K. All right. So if we multiply all those through, we end up getting 0, 100 newtons, and we get minus 75 newtons. All right. So to evaluate this integral, we can copy the next couple rows. All right. First column, first two columns of our matrix here. All right. And we can evaluate this determinant here. So what we'll end up getting is we'll get MCD is going to be equal to 30 Newton meters K, and then it'll be equal to minus negative 22.5 newtons J. So it's really equal to 22.5 newtons J plus 30 Newton meters. So it should be Newton meters, not newtons. K. And then we can find our resultant moment by adding up MAB plus MAC. So if we do that, we end up getting 60 Newton meters I plus 22.5 Newton meters J plus 30 Newton meters K. All right. So just to recap, we solved for our resultant moment. In order to find our resultant moment, we had to calculate the moments due to the individual couples at points A and B and points C and D. We could use the scalar formulation to calculate the moment about points A and B, the couple moment at points A and B, and then we used the vector formulation to calculate the moment about due to the forces applied at points C and D. And then once we had both of our vectors in Cartesian form, we could add them together to determine our resultant moment.